Hey guys, and I'm here to give you some instruction today. This is Bruce on the TPU resonator calculator. And what I've got set up here, I'm using my wife's laptop because I still have not got my desktop going. That's why those big monitors aren't lit up. And I've got my iPad over here. But I'm going to use this since this is the one that is going to be easiest for me since I have mouse control. So what I want to do is start off by talking to you about what you see here in green. Anything you see in green on the top of the page, these numbers are for your inputs. Current in amps is literally how many amps you have going through your control coils, okay, through one wire. Number of turns. Now, I have instructions here. When you mouse over this, like so, instructions pop up. So I've got instructions here that are just easy mouse over. So you just mouse over, and if you're on an iPad, you just use your finger and hold it over that, and instructions come up for each of those and tells you exactly what to do and how to do it. What I was going to say, though, is, so here I have 1 amp going through the control coil. I have 100 turns at 1 amp. My mu R, Greek letter mu, R, this is your permeability. I have here at 500. You can put it at whatever you want. Let me put it at 1,000. This is the permeability of your actual resonator. Right now, as you know, we're using what's called black iron wire, which is really an iron alloy. It's made out of carbon and steel combination, and its permeability is probably actually not 1,000. And there's no way I've not been able to find carbon-steel combination as far as permeability. But I'm using 1,000 here as my base number. Once we get into other wires, regardless of what I see, I'm going to test a bunch of wires to find out what wire works the best for our needs. And that's not going to come through guesswork. That's going to come through just steady experimentation and experimenting with a lot of different ferromagnetic wires for our resonators. So here, permeability called approximately 1,000. Iron was approximately 1 to 3,000, so I'm taking the lower numbers, how I came up with that. Readings, microhenries, 7.5, and this talks about the experiment as to how to get the inductance factor for your resonator. Simple experiment, 10 turns around the resonator, read the reading in microhenries, and just insert it right here, whatever that number is. I think, if I recall, the Rusty one came in at, I want to say, I think it was 6.5, and the non-Rusty iron, I'm not sure if it's a different metal. This would tell me it's a different permeability, a different metal, came in at 5.5. So it's interesting, even though the metals look the same, one's rusty, one isn't, it's actually a different permeability because I had a different readings in microhenries. So anyway, this tells you how to do that experiment. Very, very simple to do on your resonator. You enter that number. Your wire diameter is in millimeters. Now, this is for, I believe, 16 gauge, 1.5 millimeters. It's very, very simple. You can go to any AWG, wire AWG gauge chart or wire gauge chart, and it will give you a listing not only in American AWG, but also in millimeters. So this is based on millimeters right here, wire diameter. Now, anything in green, number-wise, is what you input. That's it. You have a total of 1, 2, 3, 4, 5 inputs. Once you input those 5 numbers, the calculator for the TPU resonator will factor in everything and put it on what I call the dashboard. Now the dashboard is down here. Now you can see I've got it all grayed out, and yours will be too, so you know that those are numbers that you simply read. You never enter anything into any of these areas. But this is your dashboard section. It says dashboard. So from here down, across, and up right here. This is a link that takes you to instructions for UH readings. Those same instructions are right there. So again, that's kind of duplicated. But right here, ampere turns, if you mouse over it, you have definitions. On the dashboard, every item has a definition right now. Ampere turns tells you exactly what it is. Magnetic field strength, what it is. Magnetic flux density, what it is. Again, you can feel free to look up the definitions more so on the net if you're wanting to really delve into something. Your magnetic flux in Webers, inductance factor, inductance microhenries, current density, reluctance of magnetic circuit, resonator length in centimeters. This doesn't change because we're working with the 15-inch TPU, so this stays the same. Permeability, okay, this is simply the Greek letter mu. This is mu-r. Don't worry, this calculates the mu for you, okay? Whole nother subject. This doesn't change, okay? As you change this, this changes right here, okay? So anyway, all this is automatic. Then if you want to say, okay, well, Bruce, how exactly did you calculate ampere turns? Well, then you come here and you simply click the link ampere turns. And if you go to the top, it actually takes you down here, but I did it on purpose, so it takes you down here, but your eyes go to the top. So on the desktop, this works. On an iPad, you might have to look for it. But anyway, it should pop up. So now the top of the page is ampere turns. And this tells you right here the formula for FM equals I times N. Okay, gives you your ampere turns. All right. So current times number of turns equals your magnetomotive force. Here is your current in amps, your turns on your toroid, your ampere turns. Then as we go back up to the dashboard again, and you say, okay, here's the B field of my resonator. Again, thinking the B field of a toroid. Now we're talking about the B field of the resonator. This is the magnetic flux density going in the amperium loop. And this is your B field. So we look at that. Magnetic flux density right here. When you click on it. Now here I have two formulas. I've got B equals mu times H, and then B equals mu naught N times I divided by 2 pi R. Okay, R is your radius. And then I've got it calculated out here, and here's your answer right here. Now yours, I've locked these so that you don't accidentally mess them up. Okay, so you don't mess up your calculator. So anyway, if for some reason you ever find a error in this, please let me know. Neither myself nor Professor Jackson are infallible. And but I did do my best to check and double check and have my friend Professor David check through it as well. So I'm pretty confident on it. I want to talk to you about what else? Oh, so okay, inductance factor. This factor is figured off of your readings in microhenry. So it's really important that you go ahead and put everything into the green box. First, have it calculated. Now, what's this going to do for the experimenter? I'll tell you what it's going to do for me. And that is this. I'm going to put in my information right here, my wire diameter. I'll have all this information. I can then go ahead and actually either save the file with a resonator name and have it and open up a new one. Or what I can do is I can simply take a picture of the dashboard that gives me all the information, especially with my iPad. Or with this, I just hit print screen and go ahead and save it as a JPEG, and I'm good to go. And off to the next resonator. So this keeps me from having to sit there, and even though this took an enormous amount of hours and time to work through, I think it'll save me time in the long run once I start slashing through all these resonators, wire diameter sizes, everything else. Hopefully, I'll start to see some trends. I'll start to say, okay, wire diameter size of X is going to work better than wire diameter size of Y. X number of turns in combination. You see what I'm saying? I'll begin to see and have a feel for what's going on mathematically. And that's one of the reasons I think that I love math so much myself, even though I'm not very good at it, is simply because it's not opinionated. It either is or it isn't. It's either right or it's wrong. It's black or it's white. And I just enjoy that very much about it. So this gives me some dead-on, straight information that I'll be able to look at as I begin to do some serious experimentation as soon as I get my little safety issues here wired in, my heat sensors and my current overcurrent over voltage. Then I'll feel safe about doing these, especially as close as I feel we are with this ferromagnetic wire. I'm not taking any chances on exploding either my house or my family or myself. As much as I love you guys, I want to take my time on the safety, make sure I get it right, and then we'll be ready to rock and roll. Then I'll be ready to move at like lightning pace going through these. So anyway, there's a lot of interesting things in here that I want to talk about. One of them is current density, and I'm going to talk about that in a separate video just related to current density. It's absolutely fascinating. Ampere turns, of course. Your current times number of turns tells you the current in the toroid or in our Amperian loop that we've got going on with the resonator. So a lot of really, really fascinating things. I think the most fascinating things that came out of doing the math on all of this for me was having a true understanding of the Amperian loop, or a better understanding of it, having a much better understanding of permeability of mu is equal to mu aught times mu r. What mu r, of course, is regular permeability. Mu aught is the permeability of free space or of vacuum, and mu is simply mu aught times mu r. It's total mu. So anyway, I understand that a lot better. That helps me in, I think, understanding if permeability plays a factor or not. I think it'll play a factor in the initial onset of catalyst in the resonator, but after that I don't think so, because the wire heats up. As your wire heats up, your permeability actually goes down. So, and as the wire heats up, the TPU begins to feed itself. I think the TPU, like I've been saying, is going to be simply a matter of current density, which I'm going to explain in the next video, as well as a matter of skin depth, which the calculation is not on here. You'll need to use a skin depth calculator, separate one for that, but a matter of skin depth, matter of wire density, both of which is directly related to your wire diameter, the number of turns are on control coil, and then making sure we have catalysts throughout and we have the right three frequencies that are unmoving and unchanging with our triangle waves. So anyway, I'm very excited. I hope you enjoy this for experimenting, and I thank you very much. Any questions that you have, feel free to put them on the board about the calculator, or feel free to PM me, or last resort email. PM works really well. So anyway, I appreciate it very much. I appreciate you guys and your support, and I look forward to hearing some feedback on this calculator. Thank you very much. Talk to you soon. Bye.